All right, we're going to start with these notes today. They're somewhat long, so I don't anticipate that we'll get all the way through them. Now that we understand significant figures, we're going to talk about some other ways to use measurements. So the objectives that we'll probably get through today is we will talk about what it means to be precise versus what it means to be accurate. So you'll need to be able to tell me the difference between those two. We will talk about how to find percent error, I believe. And then we will also look at putting numbers into scientific notation and the purpose for significant figures. All right, to begin with, we have precision versus accuracy. So accuracy is just a measure of how close a measured value is to the correct or the accepted value. So how close did you get to what we believe the right answer is? If your number is very accurate, then you got close to the right answer. If it's not very accurate, then you did not get close to the right answer. Accuracy is usually limited by human error. Okay, so either you made a mistake in your calculations, you didn't use a tool correctly, you copied data incorrectly. That's usually how we're going to affect our accuracy. On the other side of this, we have precision. Precision is measuring the degree of exactness of your measurement. So essentially, more precise answers give us more data. And this is usually limited by your measuring device. Okay, if you have a scale that can measure to 4 decimal places or a ruler that can measure, 1.325 meters, then that device is going to allow you to be more precise than a ruler that only has markings that allow you to measure 1.3 meters. And they don't know any of those further decimal places. So the more precise you are, the more detail to the exactness of your measurement you can get. So usually if we are inaccurate, that's a use problem or a skill problem. If we are imprecise, that's a limitation from the tools you were using. So you should have an image that has 4 pictures of a bullseye on it, right? This is a common tool used to show you what precise versus accurate looks like. So on the first bullseye, we have high accuracy. They were attempting to hit the bullseye. That is what we are counting as our accepted value. They hit the bullseye. They were correct. Okay? And then the high precision, they were very tightly grouped together. So if you are using a very precise measurement, your measurements should be coming out close to each other. Okay? For the second one, they were very precise, right? They got very detailed measurements, and their measurements were grouped close together, but they were not accurate. They missed the mark in terms of getting the correct answer. For the fourth one, they were much closer to the target, so they had higher accuracy, but this time their tools were not as tightly honed in, and so they had a much wider spread here. So they had low precision. And then the last one is where we really don't want to be, which is that we both missed the mark in terms of the correct answer, and also our answer was not very precise. So we didn't have good tools, and we didn't use those tools correctly. So we wound up with low accuracy and low precision. A lot of times in your common everyday life, you will hear people use the words accurate and precise kind of interchangeably because they don't realize that there's a difference between them. But in science, there is a difference. So we want to make sure we're being both accurate and precise. So when we have done an experiment, a lot of times I'm going to ask you to run a calculation called percent error calculation. Okay? And this is to measure your accuracy, not your precision. This one's to measure your accuracy. Okay? You're going to find percent error by taking your experimental value, so whatever you measured, minus your accepted value, so what the correct answer would have been, and then whatever number you get for that, you're going to divide that by your accepted value, and then multiply your number by 100 to get a percentage. So here is an example of what that would look like. Okay. Let's say I gave you a pencil and I asked you to measure how long the pencil was. And you said the pencil was, you measured it with your ruler and you said it was 10.2 centimeters long. Okay? And I told you that the box that that pencil came in said that it was in fact a 10.5 centimeter pencil. So what you're going to do is you're going to use that formula that I just gave you, and you're going to take the value you measured, 10.2 centimeters, minus the value I gave you, telling you that was the correct value, 10.5 centimeters. Then you're going to divide it by that accepted value again, 10.5 centimeters, and you're going to multiply that whole number by 100. So we should wind up with like a negative 0.3 centimeters divided by 10.5 centimeters, which, if I do the math real quick on my calculator, comes out to be, and then I take it times 100, I come out to a 2.8, should be negative, sorry, negative 2.8% error. So a negative percent error means that your experimental value was less than the accepted value. So that checks out with our example. It was negative because our experimental value was less than what the actual value was. If you come out with a positive percent error, then that means that your experimental value was more than the accepted value. So if you had measured that pencil at 10.8 centimeters, then your percent error would have come out positive. Okay, so let's do an example problem with this, okay? A student measures the mass and volume of a substance and then calculates its density to be 1.40 grams per milliliter. The correct or accepted value of the density for that gas is 1.30 grams per milliliter. What was the percent error of the student's measurement? Go ahead and try this, and then we'll run it together on the board. So to set up this problem, we're going to use our equation, 1.40 grams per milliliter minus 1.30 grams per milliliter divided by 1.30 grams per milliliter and then times 100. So 1.40 minus 1.30 comes out to 0.1. When we divide that by 1.3, we get 0.0769, which when we take it times 100 comes out to be roughly 7.69%. So our percent error was 7.69%, which means that the value we measured was more than the accepted value, which is accurate when we look at the numbers. We're about to have the bell ring, so we're going to stop here for today. You do not have any homework.